Can somebody else? Sorry, let me shift this paper. Yes. So it's not. So good morning, everybody. So last week we started the class on embedded systems. So I just gave you a brief overview to what embedded systems are and their applications, what they can do, then the basic building blocks of, and I told you the difference between a microcontroller and a microprocessor. So I told you that for embedded systems that are going to be programming microcontrollers rather than microprocessors. So this the lecture for today is going to be more hands-on. So I'll be showing you what embedded systems can do. So the different projects that can be done in embedded systems. So like we said in the last class, so we said like embedded systems are just small computers, so they perform specialized functions. So they are not doing everything at the same time. So if it's just a fire alarm, you can program it as an embedded system. So if it's a wireless security monitor, that can also be programmed as an embedded system. So if it's even a light and a bulb that you just want it to turn on and off at certain times of the day, an embedded system. So like it's just anything you want to do, but it's specialized. It's not that it's something that is doing everything at the same time. So we are going to I'll be giving you demonstrations of what embedded systems can do. And obviously, the main aim of this lecture is programming. So programming in C. So I'll just be telling you like the program behind the code. So that's basically what we are going to be doing in this class. So it's going to be very hands-on. So the first, um, so first of all, what is on the screen is Proteus. So Proteus is called Proteus ICs. So Proteus ICs is a simulation software. So it's used to simulate electric circuits. So instead of building the electric circuits like physically using transistors, resistors, capacitors, even the microcontrollers you want to use. So instead of actually doing that, what we do is that as engineers is that we first of all simulate it on a circuit simulation software to see how it works. So if it is functioning properly after simulation, then we can now decide to produce it on a printed circuit board, then actually do the implementation. So in this class, I'll be showing you both of them, the simulation in software, so produce state, then also the implementation on the circuit board. So if you have noticed, I got a lot of things there. So I'll be demonstrating both of them. So this is a circuit simulation of an embedded system. So as you can see, the embedded system has a microcontroller. So this is the P16F877A microcontroller. So like I said last week, it is a microcontroller you actually program to write the specialized code that you want to use it to do, want the system to do. So like I said last week, you have a microcontroller, which is like the brain box of the system. Then I told you that you have inputs, then you also have outputs to an embedded system. So if you can remember in the last class, like I made mention of inputs. So inputs can be sensors, they can be switches. So for the purpose of this demonstration, the input are the switches. So you can see different switches here. So these are 4 switches. So they are the inputs. So when we press this switch, something is expected to happen. So that's the input. So embedded systems, they usually have inputs for most parts of it. So like we said in the last class, in the case of the elevator, you must press a button that I'm going to this particular floor, then the lift will take you to that floor. So it's a must for most embedded systems to have inputs. So if they don't have inputs, they will have sensors that will sense the environment. So another input is this. So in circuit simulation, this is called a potentiometer. So a potentiometer is just like a variable resistor. So it's mostly used when you want to view the voltage signal of a particular system. So we can also specify it as an input because as we'll be seeing, we are going to change because a variable resistor is just, the potentiometer is just like a tunable resistor, so that you can just tune. So we're tuning this. So when we are tuning it, there will be a corresponding action. So we can consider this as an input. So this is a speaker. So in simulation, this is how a speaker is drawn. So it's a speaker, is there an input or an output? Yeah, obviously, it's an output. So when you are for instance, the fire alarm. So when you sense a fire, the fire is an input, then it's going to, the fire alarm will come on, the speaker will come on, so it begins to make noise. So that noise is like the output. So we'll be doing something like that, that will be like something is happening and there's like an alarm coming up. Then this is a display. So we call it a 7-segment display. So this display is an output because we want to be doing things to the system, and we want to be able to see that, okay, what's the input we are giving it, at least we are getting a corresponding feedback. So we need a 7-segment display to just see what's going on. So this is an output. So this is just the basic simulation of the circuit components we are going to be using. Then, like I said, we are going to be programming the microcontroller to do what we want the system to do. So I'll be, like I said, the lecture for today is going to be hands-on. So I'll be giving you examples of what this embedded system can do. Then the code is already available, so I'll be explaining the code to you. Then we'll see it working. We will even change, sometimes we will change the code. Then we will see that there's a corresponding change to what the embedded system is doing. So we'll go to this first program. So this first program is just to display it's just to display an information on the embedded system based on which switch is pressed. So let me first of all program it. So to program it, so this is the code. So let me program it. So it's to program it, I'll just say reviewed projects. Then it is building, so you can see from the screen, which says compiled successfully. So let's see the action of what this program is doing. And after that, I will go through the code to actually tell you what it's doing, so how it functions. So I'm running it by pressing this play button. I'm running the program. So the program is currently running. So what this system does is that it just displays this on the LCD, on the 7-segment display. Then when you click this button, the first button is going to change to this. When you click the second button, it's going to change. When you click the third button, it's going to change. Then when you click the last button, it's going to change. So this is just a simple embedded system. So I'm giving it an input, which is a button press, and we are seeing the corresponding output on the 7-segment display. So basically, you know how it works now. So to explain what is actually going on behind the scenes, so this is the code that is actually driving that particular system. So I'll just start from the beginning. So the first part, like this highlighted part, is just comments. So and it's displayed a comment block. So you see, this is the way you write comments. So you just put everything inside that block. So you are just telling the program that okay, just ignore everything that is inside that block. So that block is just for your use. Then this particular block of code highlighted is for the clock speed of the microcontroller. So like I specified the clock speed as 4 megahertz. So it simply means that each instruction cycle, each line of code will run at a speed of 4 megahertz. That's what it simply means. So remember I told you in the last class that an embedded system should have a clock. So the clock is just like the speed at which it runs. So for this particular, even your computer, your laptop, your desktop, even your phones, they have a clock speed at which they run. So every system, every microcontroller, every processor should have like a speed at which it runs. So like we said in the last class, the higher the speed, the faster it is, then the better for us. So so this particular line is just to set the chip configuration pin. So like I said, it's a PIC 16F8778 microcontroller we are using. So based on each microcontroller, you have to specify some configuration pins. So this is just that. Then this void LED display void is a function. Is a function in C. So in C program, we first of all have to say a template of the function. So this is the template of the function, but this is where the function is actually implemented. So this void LED display is the purpose. What it does basically is that, let me go back to the program. So you have, for the 7-segment display, you have 8 lines, 8 pins. So you can see A, B, C, D, E, F, G, and D. So these 8 lines, they correspond to some, because the 7-segment display is just 7 LEDs connected in form of a 7-segment. So this is how a single digit display works. keys. So you have the A, the B, C, D, E, F, then D, P. So if we go back to the code, this A, B, C, D, and everything you are seeing here, it corresponds to this particular, it corresponds to this. So for the one we have in this schematic, if we have 4 digits, so each of the 4 digits is controlled by these 4 lines. So when this line, this one is on, then this particular display, the first one will come on. When this one is on, the second one will come on. When this one is on, this one will come on. And when the fourth one is on, the last one will come on. So we want to be able to display the 4 digits simultaneously. So that's why we have this block of code that we connected those 4 lines to port C. So this is port C. Port C is here. So this is port C. You can see RC0, RC1, RC2, then RC3. So that block of code here is just to make sure that we display those 4 digits of the 7-segment display. We display it simultaneously so that the 4 of them can come on at once. So that's basically what the code is doing. So I wouldn't really be like going in depth to some code, but in some code I would actually go very in depth because like we have a lot of things to do. So I'm just explaining it, but if you have a question, you can just let me know so that I'll emphasize on that. Okay, so that's a good question. So you're asking for this one. So this 0x01, like I said, is for these particular 4 lines. So when you say 0x01, you are just saying that because these are hexadecimal number. So we are just using, so these are hexadecimal numbers. So you finally, this is how it is. So this is 0 and this is the 1. So this 0x01 means that you should put a 1 on 4, then 0, 0, 0. So it's just this 4 that will be displayed. So that's what the same thing means. Then if you go in depth into the code, you will see that we are shifting, we are left shifting that 0x01. So this is the first one. When you first of all input is, then we left shift is. This block of code is to left shift it by 1. So when you left shift, it becomes 0010. I don't know if you've done left shift and right shift. So you are shifting this one to the left. So it becomes this. So when you shift it, you are saying that the second LED should be displayed. So this one is going to come on. So when you do another left shift, it's 001 0 0 0 0 0. So you are saying that the third one should come on. And when you left shift again, you are doing a, so you are left shifting it. So like I said, by doing this operation, you are saying that all of these LEDs should come on. And if you look at the time period, is 200 microseconds. So because it's very fast, all of the 4 LEDs will come on at once. So you won't even know that each one of them is going on and off simultaneously. So it's doing the left shift 4 times. So that's why you have this 4 here. So because you have 4 control lines. So that's what this block is doing. Then I will go to this line of code. Here, the LED display. So this particular display is a common anode display. Is a common anode display. So common anode simply means that, so like a 7-segment display is like an LED. It consists of 7 LEDs. So you can see the 7 LEDs. So 1, 2, 3, 4, 5, 6, 7. Then a dot. That's why we call it the 7-segment display. So it consists of 7 LEDs. Then the anode of all the LEDs, they are connected together to 5 volts. So this is how it works internally. That's the internal structure. So a low voltage applied on each pin will light up the LED at that particular place. So what am I trying to say? For a common anode LED display, so you have this A, B, C, D, which I've explained by this. So this is the structure. So for instance, if you want to write a 0, so let me just draw the 7-segment display. So this is 1, 2, 3, 4, 5, 6, 7. So this is your A, B, C, D, E, F, G, and this is the dot, which is the P. So that means that if you want to write a 0, this one should be on, because the 0 is like this. So that means that A, B, C, D, E, F should be 0, because it's a common anode display. So if you have this A, B, C, D, E, F, if they are 0, if all of them are zeros, then the LED should come on. So that's why for this, to actually write a 0, so as you can see, A, B, C, D, E, F are all zeros, then the remaining are 1. So that means that to write a 0, this is the hexadecimal number you put on the code. I hope I'm clear in what I'm saying. So to write a 1, so which LED should be 0 if you want to write a 1? So B and C. So to write a 1, it's just B and C that should be 0. So as you can see, the rest is going to be 1. So B and C are zeros. Then the hexadecimal form of this is 0x9. To write a 2, so it means a 2 is like this. Yeah. So A, B, G, E, and B should be 0. So if you can see here, for a 2, A, B, E, and G, they are zeros. So this is the hexadecimal number you put in the code. So it goes on to write a 3. This, and this should be 0. So you have the corresponding hexadecimal number. So going back to the code, when we actually run the code, the default display is 5, then dash 0, 0. So when we go back to the code, the default display is 5. So this is 5. So this is the hexadecimal number for 5. So when we go back to this one, so this is 5, OX92, to write a 5. So that's why you have this OX92 here. Then this to write a dash, then this to write 0, 0. So that's how the default display is 5-00. Then going to the code, when you press switch 1, it becomes 17. So the 5 remains the same, the dash remains the same. So let me just simulate the code again. So when you press the first switch, it becomes 17. You press the second switch, it becomes 18. You press the third switch, it becomes 19. You press the fourth switch, it becomes 20. So this is what is happening. So we are just changing what is in this particular block and this particular block, because here is 0, 1, 2, 3. So we are changing what is in 2 and 3 to 1, 7. So if you look at this, OXF9 is 1. So OXF9, so this is 1. Then 7 is OXF8. So basically, this is OXF8. So when we press the first switch, which is connected to RB0. So RB0 is, because we are using, if you look at the connection, we are connecting this first switch to RB0. So this is RB0, then this is RB0. We are connecting the second switch to RB1. We are connecting the third switch to RB2. We are connecting the last switch to RB3. So that's why we have this in code. So this case is for RB0, RB1, RB2, then RB3. So basically, that's how the code works. So I can change the code. For instance, when I press the fourth switch, if I want to make it, instead of saying 20, so when you press the fourth switch, it's supposed to give you, this is 20 from the code. So maybe let me change it to 25. So for 25, or let me change to 26. For 26, I have to write OX82. So let me change this one. Instead of OXC0, let me change it to OX82, which is going to give me 26. So OX82. So basically, I wanted to write 26. So 26 is, yes, OX82. So I've changed the code. So it's supposed to, when I press that last switch, it's supposed to give me 26. So since you've changed the code, you have to rebuild the project. So after rebuilding the project, you compile it. So when you compile it, then I press the last switch. So when I press the last switch, so it is giving me 26 now. So this is how you program. So when you change things in the program, physically it's going to change on the embedded system. So you can modify the code to do whatever you want it to do by changing it. So this is a very simple program. So it's just, and I've explained the code to you. So any question, I'm going to the next program now. Can I? That table. Okay. See this particular table. So do you want to change it to something?
Can you explain like how this one, like how this one was
Okay. So that's a good question. When you understand this, it's just converting it to hexadecimal. Okay. So the way you convert it to hexadecimal, I thought you must have done that in computer programming. So Hexadecimal is like 16, so in hexadecimal form, we are converting it to like 16 base form. So in hexadecimal form, when you want to convert, so you have, if you count this, 0, 1, 2, 3, 4, 5, 6, 7, 8. So it's 8. So to convert to hexadecimal, we take it in fours. We take the bit in fours. This one and this one. So 0, 0, 0, 0 is 0. Then 1, 1, 0, 0 is C. So this is the hexadecimal conversion table. 0, 1, 2, 3, 4. So the battery is low. So this is the conversion table. So 0 in decimal form, in hexadecimal, in binary. So this is the binary, in binary form. Then this is the hexadecimal form. So 0 is 0, 0, 0. So which is 0. And 1 is the binary, 0, 0, 1, which is 1 in hexadecimal. 2 in binary is 0, 0, 1, 0, which is 2 in hexadecimal. 3 in binary is 0, 0, 1, 1, which is 3. 4 is 0, 1, 0, 0, which is 4. 5 is 0, 1, 0, 1, which is 5. 6 is 0, 1, 1, 0, which is 6. 7 is 0, 1, 1, 1, which is 7. 8 is 0, 0, 1, 0, 0, which is 8. Then 9 is 1, 0, 0, 1, which is 9. And 10 in binary is 1, 0, 1, 0, which is 8. So we don't call it 10 in hexadecimal form. So instead of writing 10 in hexadecimal, we write 8. Then 11 is 1, 0, 1, 1, and it's D in hexadecimal. 12 is 1, 1, 0, 0, and it's C in hexadecimal. 13 is 1, 1, 0, 1. It's D in hexadecimal. 14 is 1, 1, 1, 0. It's E in hexadecimal. 15 is 1, 1, 1, 1. It's F in hexadecimal. Then 16. 16 is actually going to be 8 bits instead of 4 bits. So it's going to be 0, 0, 0, 0, 1, 0, 0, 0. So normally we don't write 16 in hexadecimal. So it starts from 0 and it ends at 15. So this is binary to hexadecimal conversion table. I know you should have done that. Definitely. So looking at this table, then putting it in pause. So 0, 0, 0 is 0. So you have 0. Then 1, 1, 0, 0 is what? 1, 1, C. So that's why you have C 0. So you take the first form, 1, 1, 1, 1. 1, 1, 1 is F. So you have this F. 1, 0, 0, 1 is 9. 1, 0, 0, 1 is 9. So you have this 9. So 1, 0, 1, 0 is 8. 1, 0, 1, 0 is 8. Then 0, 1, 0, 0 is 4. So I think you now understand the logic there. Yeah. Okay, that's a good question. So it's the other way round because this is a common Untitled 7 segments display. So like I described, the internal structure of the common anode is that all the pins, the anode of all the LEDs are connected to 5 volts internally. So that means that when you apply a low voltage, that's when it comes on. The converse case or the reverse case is if it was a common cathode 7-segment display. So if it was a common cathode 7-segment display, the internal structure is that the cathode of all the LEDs are connected to ground. So this is the internal structure of the common cathode. So it means that when you apply the 5 volts on the pin, it's going to come on. So that's why, for the purpose of this illustration, is a common anode I'm using. So if it was a common cathode, it's just the reverse that is going to be the case. So it's actually when you put a 1 to it, that's when it's going to come on. So that's why you have that in it. So any other question before I go to the second code? So I guess so. Like I said, it's just to demonstrate what embedded systems can do. Then telling you the code behind it. So this is like a simple code. So when you look at the code in the C code, it's just 70 lines of code, and it's so when you see an embedded system normally, like you just feel that okay, this is like complicated, but I mean explain to you like what is actually the code behind it. You can see that it is actually something you can do because embedded systems is you're just programming just a simple, a specialized function. You are not doing too much complex work. It's just you just have a problem, a specific problem, then based on that, you solve it. You try to write an embedded system that does that. So I would explain another code for you. So this is another embedded system code. So basically, what this is doing is a counter. So let me program it. So it's basically a counter, and it is counting from 0 to 9999. So let me just demonstrate what it's doing. So this is basically what it's doing. So it's counting from 0 to the last, and it's counting it very fast. So I'll tell you why it's actually counting very fast. Then we are actually going to slow it down in subsequent code. So it started from 0, then it counts to 999, then it would reiterate again. So it's almost getting to 9999, then it's just reiterating again, and it's doing that very fast. So that is basically what this program is doing. So why is it counting? First of all, I will tell you the reason why it's counting it very fast. So like I said, every embedded system should have a clock. So the clock indicates like each line of code, the time duration is going to run. So for this particular block, I define the clock speed as 4 megahertz. So that means that each line will actually execute, the speed of execution is like 4 megahertz. So if you convert that to microseconds, so you know what that means. So that's just the basic reason why it's counting very fast. So if we can actually slow it down to specify the appropriate speed, then we'll be able to like make it to count count much more slowly. So we'll be doing that subsequently. But let me explain the code behind it. So this particular array, you've seen it before. So it's basically what you have here. It's basically what you have here from 0 to off. So this is what you have here. So you are actually specifying how the program should display 0 to off. So that's what this block of code is doing. So in any embedded system, if you can remember in the last class, we talked about registers. So you have to set a function for a particular register you're using. So you have TRISD. So TRISD is the register for port D. So if you look at this particular schematic, you can see that these lines, they are connected to D. So round is 0, round is 1, round is 7. So that's why you have this D. So you are, by saying that OX00, you are saying that all of these are outputs. So remember that the 7-segment display is an output. So you have to make the register that's to which the microcontroller is connected to, like the pins of the 7 segments to which the microcontroller is connected. So you have to make it as output because the 7-segment display is an output. So you have to specify the TRISD register as output. Then the TRISD C is specified also as output. So this is the port C. So it's also connected to 7-segment display. So you have to make it as output. Then TRISD, we are not really using, this is A, port A. So we are not really using it. So this is not really needed. Then TRISB, this OX0N. So in binary, OX0N is 0000 and 1111. So it simply means that, so because the microcontroller we are using is an 8-bit, it's 8 bits. So the register is an 8-bit register. So this is the way to count it is that it starts from 0, 1, 2, 3, 4, 5, 6, 7. So it simply means that from 0 to 3 is inputs, then from 4 to 7 is output. So it's not that every time you make all of them as inputs and outputs. You can make each particular thing an input and each particular another thing an output. So that's why we did it here. So this port B. So this port B, you can see port B here. So B0 to B3, we make it as input because it is connected to switches. So B0 to B3, we made it as input 111 because it's connected to switches. And I remember that switches are inputs. Then we connected B4 to B7. We do it as 0. That means we specify it as output. So that's what we are doing in that block of code. Then this option reg is a register for this particular microcontroller, and it sets different things you want to do. Remember that what this program is doing, when we actually run it, is to count from 0 to 999. So the way it's actually counting is that it's using interrupts. So what are interrupts? So interrupts are service runtime routines you program when you actually want to do something at a particular time, and the speed, the time you want to do it is very important. For instance, if you want to, like you are counting, and it's counting like, and the speed at which it's counting from 0 to 999 is like a very fast speed, like up to 4 megahertz. So we need interrupt to do that. So when you want something to be done at this particular time, so you want it to not to miss that particular time period. Because when you go deep into embedded systems, sometimes you use embedded systems to program real-time systems. So what are real-time systems? Real-time systems are systems that are like the deadline, the time deadline is important. So if you want the particular switch to go off at a particular time, and you don't want that time to be delayed, you don't want exact, you need to use a real-time system. So interrupts are good at that. Doing something at a very predictable time, that this thing was done at this particular time. So that's why we use interrupts. So interrupts can be programmed in using embedded systems. So for this particular program, we are programming it with interrupts. So we are using interrupts on the RDO pin, which is edge triggered on the rising edge. So in order to do that, we need to specify this option register as this value. So yeah, it's giving us 0x 0x. So the option register, where you can see the option register is specified as 0x7n. So we are programming it and use interrupts. There are different types of interrupts on a microcontroller. So this interrupt is the one for the C0 or the output for C4, CK1P. So by specifying the option register as this, so it's 0x7n. So F is 1111. We have 1111. And 7 is 0111. 0111. So if the option register, so I said it comes from 0 to 7. So by putting all these bits as 1 or 0, we are actually specifying in this configuration. So all this configuration, you can actually use them on the data sheets. So then you have the this register. So we don't actually need this for what we are doing. So let me move to this block of code. So in the last class, I told you that for embedded systems, you have to like specify the time at which it should run. Like if you just write the code and you don't specify the time for it to run, that it's just going to work for like a specific time based on the speed or the clock speed and the stop. So that's why in embedded systems, we actually use a while loop. We call it a while loop. A while loop. So the while loop in this embedded system, we start from here, then ends here. So this is the while loop. So while loop is an infinite loop. is an evening to 23 minutes. So we are telling, so when you put a block of code in a white one loop, you are telling the embedded system, because like I said, we are evening to, so you are telling the embedded system to keep on running indefinitely. So for instance, if you don't put this code, I will still explain this code shortly. But if you don't put this code inside the white one loop, which is an infinite loop, it's just going to run this line. So if you don't put it inside white one loop, it's only going to run for, because like I said, each line, because we specify the speed as 4 megahertz. So each line will run for 4 megahertz. So after that, it's going to stop. But this time we put it in a white one loop, then it's going to keep running indefinitely. So that's why when we actually run the code, you can see that it's running indefinitely. When it gets to the last number, it's going to go on again. But if you say we failed to put in inside the while one loop, then it's just going to run once. You will not even know when it's, because 4 megahertz is like a very fast speed. So your code will not even work. Because if you just run like very fast, speed of light, you will not know when it's run and finished. So that's why while one loop is important. So even that first code we did, the one that we're pressing buttons and changing the display of 7 segments. So even that was the while one loop. So what is this block of code doing? What is this block of code doing? This block of code is simply is using a for loop. So if you can see from the for loop, the for loop has a counter that starts from 0 and ends at 999. So you are simply saying that you should count from 0 to 999. So what's inside the for loop? What is inside the for loop is this block of code. So here you have this variable called this num. You have 0, 1, 2, 3, 4. So basically, this num 0. So this num 0. We have this num 0, this num 1, this num 2, and this num 3. So you have those kinds of code in there. So I'll just explain what it's doing. So for instance, if you want to display, let me say 7, 4, 5, 3. If you want to display this on the 7 segment display. So what this line of code is simply saying is that on 0, which is one of these, so which is like the last one. It means that this counter value, so in this case, which is 7453 divided by 1000. So please say 7453 divided by 1000. So 793 divided by 1000 is 7. And the remainder is 453. So on this num 0 is 7. So that means that on this particular line, the first one, it should display 7 on this. So the next line of code is this. So on the second one, which is here, it should use this computation. So it should first of all find this sign Can somebody tell me what this sign is? Modulo. Thank you very much. So this sign means modulo. So that means that we should take the modulo of 7453. We take 1,000. So modulo is simply the remainder. So when you simply divide this by 1,000 and get the remainder. So when you divide this by 1,000, the remainder is 453. So 453, you should divide this by 100. So when you divide it by 100, you get 4, remaining 53. So that means that on the second digit, you should write 4 because we got 4 there. So that means that on the second, so this is the second one. So yeah, to write 7, to write 4. Then subsequently, on this norm 2, you should find the modulo, 100 modulo. So 7453 modulo 100. So you divide this by 100. So you will get 74. Remainder is 53. So this is 53. Then after that, you divide by 10. 53 divided by 10 is 5. So that means that on this, you should put 5. Then on the last one is 7453. So I'm just doing this arithmetic. Go to 10. So the remainder, when you divide this by 10, is 3. So on the last one, I should put 3. So this block of code from this calculation we just did is just to display the numbers on the 4 digits. So that's what is simply doing. Then I've explained this one to you for the last code. So it's just to turn on each of the 4 control lines. So it's doing it simultaneously because the speed at which it's doing it is very fast. So it's actually doing it one at a time. But because the speed is very fast, you are seeing it display like as if nothing is actually changing. So when we run the code, like all of these 4 segments, all of these 4 digits, sorry, they are displayed at a time, but it's actually, we're writing it one after the other. It's not actually like displaying like everything at once, but because of the speed, it's like I said, it's 4 megahertz each line. So because the speed is very fast, that's why you are seeing it as it displays all of this like at once. So when we actually went through the maths to agree, it was just one at a time. First of all, display the first digit, the second digit, based on the arithmetic, the last digit. So, and it's doing that very fast. But as we can see, because of the speed of the clock speed, we cannot really notice that it's actually, when the computer was actually, the code behind it is actually doing it once at a time. We thought it was just doing things like at once. So that's what this program is all about. So any question? So it's using interrupts. It's using the edge-triggered interrupts to run. So that's why it's very fast. So that's all about this program. Any question based on this? Which program? I should go off. Which one? This one. Okay. Okay, that's a very good question. So this particular, okay, this first line, which is this, is to define the clock speed of the embedded system. So you are saying that each line of code should run at 4 megahertz. So if you 4 megahertz is the frequency, 4 megahertz is the frequency. So F is equal to 4 megahertz, which is equal to 4 million, equal to 4 million hertz. So the time, the period of time is the inverse of frequency. So 1 over 4 million was what's 1 over 4 million? 0.25 and 10 minus 6 seconds. So that's 0.25 microseconds. So that means that you are saying that each line of code, this line is just to define the clock frequency. Like you're just defining that after this line, after this particular line, each line of code, like this one should run for 0.25 microseconds from our calculation. This one should run for 0.25 microseconds. So every line of code should run for 0.25 microseconds, so which is like very fast. Then what this line is that, so what this line is actually means is that 200 microseconds. So the 200 is here, then this is the microsecond. So what this is saying that we should be there. After doing all of this, it should give some time delay of 200 microseconds before because this is a for loop, before going back to the for loop. So this is just a delay block that delay the line of code for 200 microseconds. So that's what yes. So yeah, there are ways we can actually do the measurements. So I'll be showing you how to actually check, because when we run it, you can see that there is an oscilloscope. So I've not really been using the oscilloscope, but subsequently I'll be using it to actually like show you that the speed at which the system is running. So you can actually use an oscilloscope to test this. Then you can actually debug. You can use a debugger. So the process calls the debugger. So all of this, like, because this lecture is just like basic introduction. So when you really want to really check the time, you go into things like debugger, step into, step through to actually measure the time. So you put debugger like breakpoints in between the code, then use an oscilloscope to measure it. So these are like advanced stuff, like master level stuff. But it's actually possible for the scope of this work is just to give you a brief overview. Like you're not really like if you want to really go in depth, then you like do another course entirely, or you just dedicate yourself with like working on embedded systems. So we'll still get to that point where we'll use oscilloscope to measure it. So let's go to the next. Let's go to the next code. So let me compile it. So let me run the code to show you what it's doing. So for this particular, what this code is doing is that when I press this switch, this particular switch, the first switch, when I press it, the 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 RGO pin is going to toggle. So I didn't actually connect anything to it. So let me connect an LED to it. So this is an LED in circulation. Then the resistor. Then the ground. So I'm connecting an LED to this RDO pin. Look at it, RDO, the RDO pin. So when am I using an RDO? So the reason why I'm using an RDO is that from the code, this is the line of code that is actually toggling. So that's why I'm connecting it to RDO. So in the code, if here was RDO1, then in the capture, I'll connect it to RDO1, which is this one. So let me run the code now. So let me run the code. So when I run it, then I press this switch, the LED is going to come on. So when I press it, the LED will come on. So it's just to turn on and off an LED lights. So you can just program this. This is just like your switch. The switch that is turning on and off the lights in any way. So you can actually, most times, you can just use analog electronics to do that, but you can actually be programmed. So when the switch is pressed, it goes off. When the switch is pressed, the LED is going to come on. So you want to ask a question? So what's the question?
An embedded system that I use
Yes.
that is programmed to continue.
Yes. Yes. Okay. So I think
like for an embedded system that I use
yes.
Let's say like a traffic light. So that is programmed to continue.
Yes. Yes. It's continuously running, like infinitely. So an embedded system should have that feature. continuously running. Like even now, like when it's not doing anything, you feel that it's not running, but in the background, it's actually running in the background. So it's on now, and it's just on because the program is saying that it should be on. So it is when you do something, it goes off. So it's off because you already told the program that when the switch is pressed the second time, it should go off. So it's still running in the background. So embedded systems are continuously running. Even when you feel that they are not working, like for now it's off, light is off, and you feel that okay, it's not working because there's no light coming on. But it's still actually, what will tell you that it's still running is that it's when you press it again. So on pressing it, it's going to, when it's not working, it's actually just waiting for an action. It's waiting for an input command. So when you press it, then that action is waiting for the content executed. Then it continues what it was programmed to do. So this system, I've already demonstrated it. So it's also making use of an interrupt. It's also making use of an interrupt, and it's the same interrupt we used in the last code. That's also the interrupt it's using. So one thing I didn't tell you about interrupts are that when you are using interrupts for embedded systems, you don't need to put it in a while loop. So if you look at this program carefully, there's no while loop in the program. There's no while loop. That infinite loop I was talking to you about. There's no that while loop because it's using an interrupt. So when you're using interrupt, you're just saying that okay, this thing should happen at this particular time. So that's what you are saying, that this thing should happen at this particular time. So and for this particular program, the interrupt is on the RVOP. The interrupt is on the RVOP. So by setting this option register, we are putting the interrupt on the rising edge of the RVOP. So where is the RVOP? The RVOP is this switch. Look at this, the RVOP, which is connected to the switch. So what this interrupt means that anytime there is a change on this particular pin, then it should toggle the LED display. That's what is basically happening. So that's why it doesn't mean a while loop. It's using an edge triggered interrupt. So because one of you asked in the last example that how do you measure the time? So you can actually use so the interrupt, like I said, is on the RVOP. So when I change, so like if you can see what I've just done. So anytime I click on this switch, the RVOP is connected to this port signal line. So just notice this green line. So when I click on this, you can see that there is a pulse on this line, which is the RVOP. So this is just making use of an interrupt. So it doesn't need a while loop. that anytime you press the switch, which is connected to how we just turn on the LED. So just toggle the LED. So you said that anytime you press the RBOP, then you toggle the LED. So that toggling, the LED is connected to the RGO, and the RGO, so this is what is actually doing the toggling. This is what is doing the toggling. So when you press it, it comes on. So this is in your computer programming, this symbol is a not symbol in your computer program, that question mark. So for instance, if previously that audio pin was 1, which means that it's on. So in the next cycle is going to not it. So what's the next operation? If it's a 1, when the non operation is performed, what does it become? Yeah, it becomes a 0. So that's why when you press the switch is the on comes off. Then when it's on and you press it again, that not operation is performed. So the not of the 0 is 1. So that's what is happening. So that is the line of code that actually controls the operation. So like I said, this is the option register to set the interrupt on the RBOP so that anytime there is anything happening on the RBOP, then this not operation should be performed. So any question before we go to the next code? So these are just embedded systems. So you program it like I said. So normally this particular code, you feel that no programming is involved, but we've actually seen that there is programming involved. So the LED, when you press it, the not operation is performed on it, and it either goes on or off. So let's go to the next code. Okay, so let me build the project. So what this code is actually doing is that it's doing the thought, the EXP3 with it. So let me run it. So it's counting So what this code is actually doing is that so from what you can see, what is this code all about? From what you can see, what is it doing? Can somebody tell me from this one part of the class? Because you people you are not listening. So what is the code doing from this? Anybody from there? Yes. I'm sure all of you are not even here in class. So what's the goal? Yeah. Anybody that wants to answer something? What? What? It's changing the color. What? Changing colors. All of you get those who know what's happening. They're not even in this class. So what this system is doing is that it's blinking the LED, this particular LED light. It's blinking it at a particular speed or frequency. From what you can see, can you guess the rate at which it's blinking, at which is doing the blinking? Can you just estimate the speed of operation, the speed at which it's blinking? You cannot estimate what's the speed at which it's blinking the LED. So, in order to measure the speed at which it is blinking, the LED is blinking, I will connect this line to the oscilloscope. So I'll connect the line to the oscilloscope so that the oscilloscope will tell us the speed at which it's blinking. So it's connected to the yellow line. So from this line, can you tell me the speed at which the LED is blinking? So it's blinking, it's coming on and off. So what's the speed? So can somebody, even don't tell me the speed, can somebody tell me how to measure the frequency, the speed at which it's blinking, from where to where? That's just what I want to know. So I just want to test your intelligence in class. For this time, because look, even the fact you guys are even worse. So from this side of the class or from the back, okay, which children? Or anybody that wants to come and tell me how you can measure the speed from this oscilloscope. So how can you measure the speed? You can see the oscilloscope is blinking at And the oscilloscope is like those people that have been doing different things, they are now looking and see they know what is happening. I mean, when they don't have an idea of what's going on, just because I decided to engage you, that's why you're now looking and you're looking at it. You actually know what is happening. So somebody should tell me how you can measure the speed. Somebody should tell me how you can measure the speed at which the element is blinking. I have the question just from the visual indication. Nobody answered. Now I've got out an oscilloscope. What's the speed? How can you measure the speed? Yeah, do you want to say something? So nobody in this class actually knows what is happening.
Yes, the distance between like forward side. That would be like distance between
Yes.
find the impact.
Yes. So you are right. So that's how to measure the speed of at which it's blinking. So I'll be telling you how we actually set the speed in the code, because it's not just doing that on its own. There is a code behind it. So the register that is being used is this register, the option register. So we are using the option register to set the speed, and we are using the Timer0 register to set the speed. So it is these two things, these two registers that are controlling the speed at which the frequency at which that LED is blinking. So from this code, the option register was set to OX07. So for OX07, paper or a roster. So for OX07, so I told you that there are two registers that we are programming to actually control the speed of thinking. So the first one is the option register. So from the code, we set the option register as OX07. So what this simply means is that so this the option register is an 8-bit register. So you have I just want to divide this into 8 bits. So this is the 8 bits 0, 1, 2, 3, 4, 5, 6, 7. So you set it as 0, 7. OX means that is hexadecimal. So when you see OX, it doesn't mean that you are working in hexadecimal. Then this is 0, 7. So 7 is 0, 1, 1, 1. Plus, so we start from 1, 1, 1, 0. Then 0, 0, 0, 0, 0. So this is what the option register is set to. So if you look at 5, 5 is set to 0. So by setting 5 to 0, because there are different types of interrupts. The interrupt we considered in the last example one is called Timer0 interrupt. Timer0 interrupt. So by setting this 5 bits to 0, you are saying that the timer code is selected. So that's why this has to be 0. Then this has to be 0 is you are setting a prescaler for the Timer0 module. Then this here is 1111. Now when it's 1111, it means that the prescaler is 12256. The prescaler of the timer module. So that's what it simply means. So I will tell you why all these are important. The formula actually to set the speed we want. For instance, if we want a 50 millisecond speed, this is the formula we will use. So this is for the option register. So in order to actually set the speed, we need to write to the TMRO register. So the TMRO register is also a 8-bit register. So it's also an 8-bit register. So 0, 1, 2, 3, 4, 5, 6, 7. Then the formula is equal to 256 minus period times FOSC divided by prescaler times 4. So the period is the period you want, the frequency, the period you want the enemy to take. So you have to write the result you get from this calculation has to be written into the TMRO register in order to set the speed or the frequency of thinking. So for instance, if you want the speed to be 50 milliseconds, so this period is going to be 50 milliseconds. So this FOSC is the frequency, is the oscillation frequency. So can somebody tell me, from what we've been doing so far, what's going to be the frequency of oscillation? What's going to be the frequency of oscillation? Yes, 4 megahertz. Then the prescaler, by setting this 1 to 111, you have a prescaler of 256. So that means that when you do this calculation, 256 minus 50 milliseconds times 4 megahertz divided by 256 times 4. When you do this calculation, you are going to get 61. So that means that it's 61 that you write into the TMRO register to have a frequency of 50 milliseconds. So 61 is in decimal. So you have to convert it to hexadecimal. So can somebody do the hexadecimal conversion? You can just use your calculator if you can do that. You convert from 61 to hexadecimal. So let somebody do that. 3D. Okay, thank you very much. So the hexadecimal form is 3D. So that means that you are going to write a D here and a 3 here. So D is 1011, then 3 is 1100. So that means that for the TMRO, this is what you are supposed to write. So that's for 50 milliseconds. So in this example, in this particular code, it's 16 milliseconds. So that simply means that so the battery is low, this one can get another battery. So it's 16 milliseconds. So we just put 16 milliseconds air. So when we do the calculation, as somebody do the calculation, just put in 16 milliseconds. What's the answer when you put 16 milliseconds in? Somebody from this part of the class and the back. Well, the back are in millions. You are able to trying to dash. Well, you guys are just confused. Yeah, what's the result of the calculation? Yeah. So for this 16 milliseconds, what you actually do is that 256 minus 16 milliseconds is 16 times 10 minus 3. Then 4 megahertz is 4 times 10 6. Then divided by 256 times 4. So I need another battery. This battery is low. So what's the result of this calculation? Huh? What's the result of that calculation? 193.5. So 193.5. So let's just make it 193. So the hexadecimal form of 193 is what? From your calculator. What's the hexadecimal form of yeah? Yeah. This one is practically on this one. But you have to do this one first. Then you have to subtract from which one did you do? What's the hexadecimal form of C1? Okay. So that's why we put, it's actually supposed to be, because it's approximated, so that's why I just put C3 here. So when you actually measure the period, so the period of blinking is 16 milliseconds. But actually, when you look at the code, because 16 milliseconds is really very, is really, so 16 milliseconds is really very fast. So it's slow. So in this particular line of code, I delayed it by 30. So the speed is actually, the speed of operation is actually 16 times 30. So 16 times 30 is 480. So the speed at which the LED is blinking is 16 milliseconds times 30, which is 480. So it's 480 milliseconds. The 16 milliseconds is very fast. So that's why I have to slow it down by making it 480 milliseconds. So when we actually run the code, the speed or the frequency is about 480 milliseconds. So how do you measure it? So you measure it from this window. So from the oscilloscope, from here to here is 100. So 100, 1, 2, 3, 4, 5, 6, 7, 8, 9. So then there is a little bit of offset here. So because from here to here is 480, from here to here is 480. So the speed is actually 480 plus 480 is what? 6. Yeah. So this from here to here is actually 690 approximately, because it's 100, 200, 300, 400, 500, 600, 700, 800, 900. Then a bit of offsets. So that's 960 milliseconds. So when I was asking you what is the speed at which it is blinking, is about 480, 490 milliseconds. Then even from observation, like 960 milliseconds is about 1 second, because it's 100 milliseconds equal to 1 second. So if you look at it just by visual indication, it goes on and off every 1 second. So you can actually use, that was what I was asking you first in the first instance, that what is the speed? Like after 1 second, it goes on and off. So you can use programming in order to set the period of the period at which an LED blinks. So we can also use so when I did the one for 50 milliseconds, we got 61, and 61 is 3D. Set 61 is 3D. So if I'm to put like 3D here, it's going to be 50 milliseconds. So 50 times 30 is going to be 1,500 milliseconds. That's 1.5. So let me just put it. So when we did for 50 milliseconds, we got 3D. So I'm writing 3D into the Timer0 register. Then when you can see that it's from the oscilloscope. So 100, 200, 300, 400, 500, 600, 700, 800, 900. So it's still about the same thing. Let me okay. I also need to change it here to 3D. So when I changed it, so you can see that even from observation, it's more slow. So 50 times 30 is like 150 seconds, which is 1.5 times 2, that's 3 seconds. So the frequency at which this is blinking is 3 seconds. So from the oscilloscope, you can, let me change the scale to 200. So we are measuring, just need to measure from there to there. So That's the way we actually got that. So that's the way we actually got that. Then, so that's that for the frequency. So you can also use, it's not only LED, you can also make use of, motto. So you can actually, because you can set the period of a DC motto. So when you are actually making use of a motto, so this is a motto. So I want to ask a question for the class. Like, if I have a DC motto, then I want the motto to move very fast. So let me ask this question before I actually demonstrate it. So if you have a motto, I want the motto to move at a very high speed. So the frequency, should it be high or low? I want the motto to be turning like the fan now. The fan is controlled by the DC motor. So for instance, if you want to program a fan and you want the fan to really go very fast. So my question to the class is the frequency at which it is moving. So before I look at the question, I want to tell you that the speed of the fan is controlled by the frequency. So you use a frequency an interrupt that generates a particular frequency to control the speed. So speed is controlled by the frequency. That's, I'm telling you now, it's controlled by PWM, which is like a pulse width modulation. So my question to the class, to this particular side of the class, I know you won't answer, but we have to. So my question is, if I want the speed of the fan to be very fast, the frequency, should it be high or should it be low? That's my question. It should be high. Thank you. Sorry, I thought you wouldn't get it. Well, thank you for that. So if you want the frequency to be, if you want the speed to be very fast, you set the PWM, the frequency of the signal, you set it to be very high. Then if you want it to move very slowly, the frequency is going to be very low. So for this particular code, like I said, the frequency is 3 seconds. So that's very slow, very slow. 3 seconds is about 0.33 hertz. So that's very slow. So we should see the DC motor moving at a very low speed. So DC motor is turning slowly because the frequency of operation is 3 seconds. And 3 seconds is equal to 0.33 hertz, which is very slow, very, very slow. So let me increase the speed because originally it was C3. Let me make it C3 just to make it fast. It's from this formula I'm using. I already explained. So let me make it C3. So C3 is like 1 second. So 1 hertz. So now I'm make it 1 hertz, which is 8 bits faster. So if I do, let me program it again. So let me use it. So this is a little bit faster than what we had previously. So now let me make it really, really fast. Let me make it 16 milliseconds. So let me make it 16 milliseconds. So 16 milliseconds is equal to how many hertz? 16 milliseconds is equal to how many hertz? Huh? What's 16 milliseconds? What's 60 milliseconds in hertz? 62.5. So let me make it very fast. So 62.5 hertz. So let's see how the DC motor moves. So it's still slow, and the reason why it's slow is, let me make it so. So it's not really changing here, but it's actually supposed to go faster. So the frequency is not actually changing here because it's still the same thing. So the speed of the motor is actually supposed to move faster because we changed the frequency of operation, the frequency of the pulse width modulation. So when you are actually changing the pulse width modulation, is actually the frequency that you are setting for the either an LED light or a DC motor. So it's actually supposed to the speed of the motor is actually supposed to go faster. So for the next, any question based on this? No question. So we'll move to the next one. So this particular one is basically what is happening in the previous one. It's also using a Timer0 interrupt. And it's just that it's using the interrupt to count from 0 to 199, but at a much slower pace. And the speed at which this is counting is 65 milliseconds times 20. So 65 milliseconds times 20, which is equal to 130 milliseconds. So it's counting from 0 to 199, but at this particular speed of operation. So let me review. One three zero zero, which is 1.3 seconds. So let me so you know the one we did previously, it was like there's a glitch. Let me restart. There's a glitch. So, like I said, based on the TMRO register, so based on that, you can use it to set the period or the frequency. So, in this particular example, so in this particular example, it's counting the TMRO register. Let's look at it. It's set to 0x5. It's set to 0x5. So 0x05. So the TMRO register is set to 0x05. But the option register is set to 0x07. So this is 0x07. But we set the TMRO register to 0x05. So based on that, from this formula, that means that if you do the calculation, you put a 65 millisecond and you do the calculation and you convert it to hexadecimal, then you're going to get 0x05. So based on this, is a 65 millisecond, but we are delaying it further by 20. So that's why I said 65 times 20. So that's 1.3 seconds. So the frequency of the rate at which it counts is much slower. So every like 1.3 seconds. So when it's counting it's counting very slowly. I don't know if there's something wrong with it. So it's counting very slowly. So and it's 1.3 seconds. That's the speed of operation. So I guess you all understand that. So we move for something different, which is USAT. So in the last class, who can remember the full meaning of USAT? Universal. Universal. Okay. So the universal synchronous physical transmitter. So it's used as a communication protocol in microcontrollers. So, like I said, it's basically used for transmission and reception in microcontrollers. So this, I will not really actually go in depth, but if you want to program the microcontroller for USAT, so if you want to program the microcontroller for USAT, so you need the following registers. So setting the following things, and these particular registers, the SPBR2. So it used to set the bound rates. So the bound rate is like the frequency, the speed at which you're able to receive or transmit characters on the serial terminal. So it's mostly made use of in serial terminal when you want to like display information on the serial terminal. So this is how to specify the big ways into this register. Then you have this register, CXSA, the transmit register for the asynchronous module. Then RC is receiver transmitter. So it's receiver register for the receiver module. So basically, that's how you set it. Then let me just demonstrate. So this is just to transmit characters over a serial monitor. So I'm transmitting the following characters over this virtual terminal. So this is actually where I'm typing the characters, and it's being received at this particular terminal. So if you look at the connection, the this is where I'm transmitting it from RC7. Then this is where it's the virtual terminal where it's being received. So basically, you use it when you want to display information on a sensor, or maybe the information of the sensor. You want to be able to see it. You want to be able to display it on a virtual terminal. So let me go very fast to the next one. So this one is the potentiometer. So let me just demonstrate what it's doing. Then I will ask you, let me just show you what it's doing. Then I would ask you that what is the program actually doing, just by my demonstration. So I'm demonstrating now, then I will ask you what the program is doing. So just look at what I'm doing. Okay, so I've demonstrated now. So can somebody tell me what's happening? Somebody from the side first, or from the back. So what is it all about? What's this embedded system? What's it doing? What's it all about? Okay, so if nobody can tell me, let me just move on. So I'll go to the next one. So the next one, I'll demonstrate. If you cannot tell me, then just keep moving on. So the next one is so I'm changing some things. Then let me reprogram it so you can see what I've changed. Let me reprogram it. Then let me run it again. So what's happening? Can somebody tell me? Nobody. Let's move on. So let's move on to the last one. So the last one is, so let's move on to the last one. So what's going on in this last one? So what's going on in this last demonstration? Okay. So nobody can tell me. All right, so this is the last demonstration. So the next one is just to show you because uh, we've done the simulation of embedded systems. So we've done them in software. So like I said, so when you do it in software, then you would also have to actually implement it on um, a printed circuit board. So you actually produce the system on a printed circuit board. So like you can see, I've actually brought out the implementation of the system on a printed circuit board. So I will just show you the demonstration. So all the demonstration that are being done in software. So it's just to show you that you can actually produce them. It's not just in software. Embedded systems are like real systems. So they are not it's not only in simulation. So you can actually go ahead and actually build those systems. So like this particular one now, the implementation of this is on this circuit board. So the switches you are seeing here, they are all the switches. Then this is the microcontroller. That's this big microcontroller. So this is what you have here. So these are the switches. Then this is the 7-segment display that actually does the display. So I will just show you how you can actually program the system. It's not only in simulation that you can do it. So you can also do it real life. So because embedded systems are like real systems. So so to actually program an embedded system, you need a debugger. So this is a debugger. It's called a picky tree. So you load the program. You load the program from the computer. So you load it into the board. So this is the debugger that does that. Then you actually produce this on a board. So I think by the time you do a course in your, probably your 300 level on producing embedded systems on a printed circuit board. So you can, you should be able to do that. Then I'm using MP Lab to actually do the program. So this is another software. So for instance, the first program we wrote. So let me open it here. So this is a picky tree, like I said, that does so if somebody can come and hold this camera so that the whole class can see it. Can you just hold it so that they can see what's happening? Okay. So this is the board here. So the actual implementation of it. So like I said, this is the PIC microcontroller. Then this is the programmer. So this is the programmer. So you transfer the code from the computer to the board using the programmer. Then in order to program it, so this is the first program. So this is the same first program we used. So in order to program it, you just do the same thing. So it's programming. Then when you actually look at it, so this was the program we wrote on the, this was the program we wrote, if you can remember, those people that were following. So this was the program we wrote. Then when we press the first switch, it changed to 17. We press the second switch, it changed to 18. It changed to 19. Then it changed to 20. So you can actually see embedded systems are real systems. So the second program is yeah. Yes, yes. Thank you for the observation. So it's just because of the speed. So in order to stabilize it, you just need to reduce the speed. Then this was our second program that was counting. So it was counting from was counting from 0 to 199. So it's counting very slowly. So this was the program so I actually explained this program to you. Then I will just go through all the whole. So for this program, it was when we pressed the switch, the LED, it came on and off. So if you press, so this particular LED, so when we pressed it, it came on. Then when we pressed it, it came off. So that's the demonstration for this one. Then the next, so this was the case of the blinking LED. So that was blinking at a particular frequency. So like I said, you can connect a DC motor to it, to maybe a fan, to control the speed of the DC motor. Then the other one, this was the same one as counting, but this counts much faster. So I've tried to explain the code behind it. So this particular code was the one I explained that nobody refused to answer. So there is a potentiometer. There's a potentiometer here. So when you actually vary the potentiometer, you will see some variations on the LED screen. So we also demonstrated that one. So the purpose of all of this is just to prove to you that embedded systems don't only work in simulations, they are real systems. So the mind is just the imagination. Once anything you conceive that, okay, I want to program this, then it's actually possible to actually do the programming. So this is the last one. So you have a buzzer. So there is a buzzer. This is the buzzer here, where my finger is. So this is the buzzer. So you can begin to think of the applications like a fire alarm system. Maybe you have a fire sensor attached to it. So when there's a fire, the alarm begins to go to come on, to go off. So these are the embedded systems and real systems that you can program in real life. So there are other things you can that you can actually use to program embedded systems. So this is the PIC microcontroller. So there are other programmers, there are other microcontrollers that can be used to program embedded systems. So one of them is the microbit. So if you can see, yeah, so this is a microbit. So it's another kind of microcontroller. So the microcontroller it uses, look at its size. When my finger is pointing to, that's where the microcontroller is. So it's very small. So microcontrollers are not like, they have to be very, very big. So they can be as small as this. So this kind of a microcontroller can do the same thing, even more than what the PIC, the one we have been using to program. It can even do more than that. So this is what we mean by embedded systems. So they are very small controllers that can be able to do specialized tasks. Then you also have this another kind of microcontroller. So it's the PIC 16F876A microcontroller. So it's just based on what you've been doing, the 7 segments. It has the microcontroller, it has a speaker, it has a switch. Then this blue is the crystal oscillator, it's the clock. So like I said, every embedded microcontroller should have a clock. The rate at which each instruction cycle moves. So this is the clock for this. So you can design it on a small scale like this. So you can just design an embedded system that does a particular task you want it to do. Then for this microcontroller, this is the crystal oscillator, the clock. For this one, this is the crystal oscillator. Yeah. So every embedded system should have a clock at which it operates. So like I said, it just depends on what you want to do. So you can, once you have the interest, thank you very much. So once you have the interest, so you can actually like do anything you want it to do just by programming it. So this is just like a tip of the iceberg. So you can program in C to do as many things as you want to do. So as many things as you feel like doing. So if, like I said, if you want to build an elevator, it's based on an embedded system. So a wireless security monitor, baby trackers, heart rate monitor, all of these systems, even your phone is based on an embedded system. So you can program it. So we focus on programming in C. So majorly this course is on programming in C. So there are other programmers, there are other platforms. There's the Arduino. So in Arduino, it's much more, it's not as complicated as this, but C is once you can program in C, then like C is like the programming language is like assembly. So it's assembly language. The computer understands assembly language and it programs it faster using assembly language. It's just that assembly language is very difficult to understand. So the better option is C. So C is much more friendly, but it also compatible with hardware, with microcontrollers. So we have programmed with C. So there are other forms that there's the Arduino. So Arduino is like very simple form of programming. You don't need to go into the register level because here we're manipulating registers and everything. You just write instructions that are like almost similar to the way human language works. Then we have the Python. So Python is very like it's a high-level programming language that can be used to program microcontrollers. So it just depends on which you want to use. So this lecture is just to give you the understanding that you can actually program embedded systems. Then there are other courses in your 300 level, like I was saying, to actually build a PCB board, to translate from the schematic to the PCB board. There are courses you will do to do that. Then to actually program, there are courses in your 400 and 500 level. Then to do like other forms of programming. Then like to really know what's going on. Then those are more advanced courses. So this lecture is just to introduce you just to that the embedded systems you see all around you. So this is where they started from. First of all, you start with simulation, then you actually program on the device, and most especially you use the C language or any other compatible language that you want to use. So are there any questions? Okay, no questions. Thank you. So this will be this is the end of the for the class for today. So so this is like the final lecture for the class. Then so we are done with the class. Thank you very much for your attention.